Hello, friend. Welcome back to this quiet corner of the universe where science softens into wonder and facts drift gently into dreams. Some nights when the world grows still, you might notice something strange. The way a leaf spirals slowly to the ground, the way water finds its level in a glass, the way your own body settles into the pillow beneath you as if the earth itself is holding you close. There's something pulling at everything always, something invisible, something older than mountains, older than stars. We call it gravity. But what if I told you that gravity isn't really pulling at all? What if the universe has been whispering a different secret all along? Before we drift into this invisible architecture together, if you find comfort in these quiet journeys through science and sleep, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. No pressure? Just an invitation to rest here whenever you need. Now, let's drift. Tonight, we'll walk through the force that holds galaxies together and pulls raindrops to Earth. We'll trace the invisible threads that shape everything from the curve of space-time to the beating of your heart. You don't need to understand everything. Just rest and let gravity do the holding. Imagine standing in an open field at twilight. Above you, stars begin to prick through the darkening sky, ancient and endless. Beneath your feet, the earth turns steady and sure. You feel grounded, held. But here's the beautiful strangeness. Nothing is actually touching you from below with force. The ground isn't pushing up. Gravity isn't pulling down. Instead, you're falling constantly through curved space, and the Earth is simply in your way. Scientists suggest that what we experience as gravity is actually the shape of the universe itself. Mass bends space and time the way a heavy stone bends the surface of a trampoline. We don't fall because something pulls. We fall because we're following the natural curve of existence. It's as if the cosmos is a fabric, and everything with mass creates a gentle valley in that fabric. We slide into those valleys not because we're forced, but because that's simply where the shape leads. Think about that for a moment. Right now, as you rest, you're not being held down by a force. You're tracing the curvature of space-time itself, moving through 4 dimensions in a dance so constant, so intimate that you've never questioned it. Until now. The ancient Greeks felt this pull, though they couldn't name it. Aristotle believed that heavy things fell faster than light things, that objects yearned to return to their natural place in the cosmos. For nearly 2,000 years, this idea held. It seemed true. Drop a stone and a feather, and the stone races earthward while the feather drifts and tumbles. The evidence appeared obvious, but the world is full of gentle deceptions. Around 350 BCE, Aristotle taught that a 10-pound weight would fall 10 times faster than a 1-pound weight. It made intuitive sense. Heavier things feel more substantial. They should fall harder, faster. But intuition, it turns out, is just pattern recognition wearing the mask of truth. And sometimes the pattern we recognize is wrong. The error persisted for centuries, woven so deeply into human understanding that questioning it seemed almost absurd. Why would anyone doubt what their eyes so clearly showed? But then all revolutions begin with a simple, uncomfortable question. What if we've been looking at it wrong? In the late 1500s, a mathematician named Galileo Galilei began to wonder. There's a famous story, perhaps true, perhaps not, that he climbed the Leaning Tower of Pisa and dropped 2 spheres of different masses from the top. Observers below watched them fall, and they landed at the same time. The myth may be more poetic than literal. Galileo probably never performed this exact experiment from that particular tower, but what matters is that he thought it through with careful logic. He realized that if Aristotle were right, 2 stones tied together should fall faster than 1 stone alone, because together they weigh more. But wait, if they're tied loosely, should the lighter one slow down the heavier one? And if so, how tightly must they be bound before they fall as one? The contradictions multiplied, and in those contradictions, truth began to breathe. Galileo rolled balls down, inclined planes, instead slowing their fall enough to measure. He discovered that all objects accelerate at the same rate, regardless of mass, at least when air resistance is removed from the equation. The feather falls slower, not because it's lighter, but because the air catches it, cradles it, slows its descent through friction and form. In a vacuum, the hammer and the feather fall together. This was proven definitively in 1971 when astronaut David Scott stood on the airless surface of the moon and dropped both. They touched the lunar dust at the exact same instant. Two objects wildly different in shape and substance, obeying the same invisible rule. It's a small thing maybe, a hammer and a feather. But in that moment, humanity glimpsed something profound. The universe doesn't favor mass. Gravity treats the fragile and the solid with equal attention. There's something almost tender in that, don't you think? But even Galileo, brilliant as he was, didn't know what gravity actually was. He described how things fell. He measured their acceleration, 9.8 meters per second, squared here on Earth. But the why remained hidden like a word on the tip of the tongue, just out of reach. Then came an apple. Or so the story goes. In 1666, a young man named Isaac Newton sat in a garden in Woolsthorpe, England, escaping the plague that ravaged London. Some accounts say he watched an apple fall. Others say he simply pondered why the moon didn't fall the way apples did. Either way, something clicked in his mind, a connection so simple and so vast that it would reshape human understanding for the next 3 centuries. Newton realized that the force pulling the apple to the ground was the same force holding the moon in its orbit around the Earth, the same invisible hand guiding planets around the sun. Gravity wasn't just earthly, it was universal. He called it the universal law of gravitation. Every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. In simple terms, the more massive something is, the stronger it pulls. The farther away it is, the weaker that pull becomes. Imagine 2 dancers spinning slowly around each other in a vast empty hall. The closer they are, the tighter their orbit. The farther apart, the looser the connection until eventually they drift beyond each other's reach. That's gravity. A dance of mass and distance, silent and eternal. Newton's equation F equals G times m1 times m2 divided by r squared was astonishingly accurate. It explained why planets moved in ellipses, not circles, why the tides rose and fell with the moon's pull, why comets traced long, lonely arcs through the solar system before returning centuries later right on schedule. For the first time, humanity could predict the heavens with precision, eclipses, planetary transits. The return of Halley's Comet in 1758 exactly as Newton's mathematics foretold, 16 years after his death. The cosmos wasn't chaotic. It was a clock intricate and reliable, ticking according to rules we could finally read. But not everyone believed him at first. Some scientists questioned whether an invisible force could act across the emptiness of space without any medium to carry it. How does the sun reach across 93 million miles of nothingness to hold the Earth in orbit? Newton himself admitted he didn't know the mechanism. He simply described the effect. "I frame no hypotheses," he famously wrote. He gave us the math. The why once again would have to wait. Still, his law worked, beautifully. For over 200 years, Newtonian gravity remained the foundation of physics. Engineers used it to build bridges. Astronomers used it to discover Neptune, finding the hidden planet, by observing wobbles in Uranus's orbit gravity's signature written in motion. Even today, we use Newton's equations to launch satellites, navigate spacecraft, and predict the paths of asteroids. But here's the thing about truth in science, it's not fixed, it's layered. Newton wasn't wrong, he was incomplete. And in 1915, a quiet physicist with wild hair and a thought experiment would peel back another layer, revealing something even stranger beneath. His name was Albert Einstein. And he didn't just refine gravity. He reimagined it. Einstein proposed something radical. Gravity isn't a force at all. It's geometry. The presence of mass doesn't pull on other objects. Instead, it warps the fabric of space and time itself. Imagine placing a bowling ball on a trampoline. The surface curves around it, creating a depression. Now, roll a marble nearby. It doesn't fall straight toward the ball because the ball is pulling it. It falls because the surface is curved and the marble is simply following that curve. This is what mass does to space-time. The sun doesn't pull the Earth. The sun curves space-time, and the Earth moves through that curvature, tracing what we perceive as an orbit. You're not stuck to the ground because gravity pulls you down. You're following the curve that Earth's mass creates in the fabric of reality. It sounds impossible, poetic even. But in 1919, during a solar eclipse, scientists observed starlight bending around the sun exactly as Einstein predicted. Light, massless, swift, still follows the curves of space-time. The universe had confirmed it. Space and time are not separate static things. They breathe, they bend, they flow. And we move through them like rivers following valleys we cannot see. Does that change how it feels, knowing this? That you're not held, but guided. That the invisible hand is not a hand at all, but the shape of existence curving gently around you, always. So, here we are, resting in the quiet, held not by force, but by curvature, falling not down, but forward through time. The same principle that keeps your feet on the floor also keeps the moon circling overhead, keeps galaxies spinning in the dark, keeps the universe expanding into itself. Gravity is the invisible architecture, the blueprint beneath everything. And now, as we settle deeper into this night, we'll begin to trace its hidden rooms one by one. From ancient thinkers who felt the pull but couldn't name it to the moment, light itself bowed to the curve of space. We'll walk through the mysteries still unsolved, the questions still whispered in the dark. But that comes next. For now, just breathe. Let your body sink a little deeper. Feel the earth beneath you, not as a solid thing, but as a curve in the cosmos. You're exactly where you're supposed to be, held by the geometry of existence itself. And that geometry is about to show us something even more beautiful. Long before Newton sat beneath his apple tree, long before Galileo questioned Aristotle, humans looked up at the sky and wondered why things fell. They felt the pull. They watched stones drop into wells, rain descend from clouds, and rivers carve their way downward through mountains. Gravity was everywhere, nameless and constant. But understanding it, that would take thousands of years of watching, wondering, and getting it beautifully wrong. Think about this. Somewhere in ancient Mesopotamia, around 3000 BCE, a farmer watched the moon rise over the Tigris River. He didn't know what held it in the sky. He didn't understand orbits or mass or the curvature of space-time. But he noticed something remarkable. The moon returned night after night, tracing the same slow arc. The stars wheeled overhead in patterns so reliable you could plant crops by them, navigate deserts, mark the passage of seasons. There was order in the heavens. Something invisible was keeping everything in place. The Babylonians were among the first to record these patterns with mathematical precision. They tracked Venus across the sky for centuries, noting its appearances and disappearances with such accuracy that their clay tablets still astound astronomers today. They saw the planets wander, planets the Greeks would later call them, meaning wanderers, and they wondered what unseen force guided those wanderings. They didn't have the word gravity, but they felt its whisper in the regularity of celestial motion. It's humbling, isn't it? To realize that 4,000 years ago, people stared at the same moon you see tonight and asked the same question, what holds it there? In ancient India, around 500 CE, a mathematician and astronomer named Aryabhata proposed something startling. He suggested that the Earth rotates on its axis, and that this rotation combined with some attractive force kept objects from flying off into space. He didn't call it gravity. He called it something closer to the force that pulls things toward the center. But the idea was there flickering in the dark like a distant star, an invisible attraction holding the world together. Aryabhata calculated the Earth's circumference with stunning accuracy. He understood eclipses not as omens from angry gods, but as predictable shadows cast by celestial bodies. He was working with geometry and observation, feeling his way toward truths that wouldn't be formally proven for another 1,000 years. His work was largely forgotten in the West, buried under centuries of different assumptions. But the insight remained preserved in Sanskrit texts waiting. Meanwhile, in ancient Greece, Aristotle was constructing a different framework entirely. Around 350 BCE, he declared that objects had natural places in the universe. Earth and water belonged at the center. Air and fire rose upward. Heavy things fell because they sought their natural resting place. Light things floated because they were trying to escape. It wasn't gravity exactly. It was cosmic desire. The universe, in Aristotle's view, was morally organized. Everything knew where it belonged and moved accordingly. A stone fell because it yearned for the earth. Smoke rose because it longed for the heavens. The cosmos was alive with purpose, and for nearly 2,000 years this idea held. Not because it was correct, but because it felt true. It matched what people saw every day. Heavy things do fall faster than light things, at least when you drop them in air. A rock plummets, a leaf drifts. The evidence seemed overwhelming, but here's the trap. Sometimes the most obvious explanation is just the easiest story to tell, and humans love a good story more than they love uncomfortable questions. Aristotle's physics became dogma. The Catholic Church adopted it, wove it into theology, made questioning it dangerous. To suggest that heavy and light things might fall at the same rate was to contradict not just a philosopher, but the structure of heaven and earth as ordained by God. Galileo would later face the Inquisition, partly for this reason, not just for saying the earth moved, but for suggesting that the natural order wasn't quite so natural after all. Think about how long that error persisted. 2 millennia. 60 generations of human beings watching objects fall and never quite seeing what was really happening. Why? Because air resistance is invisible, because our eyes deceive us gently constantly, because sometimes the truth requires stripping away the world to see the principle beneath. In China, around the same time Aristotle was teaching in Athens, philosophers were developing their own cosmology. They spoke of qi, the vital energy that flows through all things, and of yin and yang, the complementary forces that shape existence. They didn't frame it as gravity, but they understood balance the way heavy and light up and down work together to create stability. The Taoist text, Huainanzi, describes how all things seek equilibrium, how water finds its level, how the heavens and earth support each other in dynamic tension. Different words, different frameworks. But the same observation, something holds the world together, something we can't see but can always feel. The Islamic Golden Age brought new precision to these old questions. Between the 9th and 13th centuries, scholars in Baghdad, Cairo, and Cordoba translated Greek texts, preserved Indian mathematics, and conducted experiments that would lay the groundwork for modern physics. Al-Biruni measured the Earth's radius by observing the horizon from a mountaintop. Ibn al-Haytham questioned Aristotle's optics and proposed that light travels in straight lines, a small insight that would later help explain how gravity bends those lines around massive objects. They didn't discover gravity, but they refined the tools needed to eventually see it: the astrolabe, trigonometry, experimental method. The idea that nature could be measured, tested, questioned without invoking divine whim at every turn. Still, the question remained, why do things fall? By the time the Renaissance arrived in Europe, cracks were forming in Aristotelian certainty. Nicholas Copernicus in 1543 suggested that the Earth wasn't the center of the universe at all. The sun was. This shattered the idea of natural places. If Earth is hurtling through space, spinning and orbiting, then what's pulling us down? Why don't we fly off into the void? Copernicus didn't have an answer. He simply moved the furniture of the cosmos and left others to explain why it didn't all collapse. Then came Tycho Brahe, the Danish astronomer, with a metal nose and an obsession for precision. In the late 1500s, he built the most advanced observatory in Europe and spent decades mapping the heavens with unprecedented accuracy. He didn't believe Copernicus was right. Tycho thought the Earth stayed still while everything else moved around it. But his data was impeccable. After his death, his assistant Johannes Kepler inherited those observations and found something hidden in the numbers. Kepler discovered that planets don't orbit in perfect circles. They move in ellipses with the sun at one focus. Their speed changes depending on how close they are, faster when near, slower when far. These weren't arbitrary quirks, they were laws. Mathematical, predictable, universal. But Kepler didn't know why the laws worked. He suspected some magnetic force emanating from the sun, pulling planets along invisible threads. He was close, so very close. What's fascinating is how many people almost saw it. Aryabhata, Kepler, even Robert Hooke in England, who suggested in the 1670s that gravity might weaken with distance according to an inverse square law. Hooke wrote letters to Newton proposing this idea, hoping for collaboration. Instead, it sparked one of the bitterest rivalries in scientific history. Hooke believed he deserved credit for the insight. Newton believed Hooke was a pest claiming glory for vague hunches, without doing the hard mathematical work. The truth, as usual, is somewhere in the middle. Science is never one person's triumph. It's a chorus of voices arguing, building, refining. And sometimes the loudest voice isn't the one that had the first idea, it's the one that proved it beyond doubt. But we're getting ahead of ourselves. Before Newton could prove anything, he had to see the question clearly, and that takes us back to the garden, to the plague year, to the apple. Or does it? Here's a secret historians love. The apple story is probably apocryphal. Newton himself told different versions of it late in life, decades after the event. Some accounts have him indoors staring out a window. Others have him drinking tea. The apple may be a narrative device, a way to make abstract insight feel human and touchable. But the core truth remains. Sometime around 1666, isolated in the countryside, while London burned with disease, Newton asked a simple question. What if the force that makes apples fall is the same force that holds the moon in orbit? It's such an obvious question now that it barely sounds like genius. Of course the same rules apply everywhere. Of course the universe isn't divided into earthly physics and celestial physics. But in 1666, that unification was revolutionary. Heaven and earth governed by one law, the mundane and the cosmic braided together by invisible mathematics. Newton worked in isolation for years, developing calculus to handle the equations, testing his ideas against Kepler's observations, checking and rechecking. He didn't publish immediately. He was meticulous, secretive, reluctant to expose his work to criticism. It wasn't until 1687, 20 years later, that his masterpiece appeared, Philosophia Naturalis Principia Mathematica, the mathematical principles of natural philosophy. In it, he laid out the universal law of gravitation. Every particle attracts every other particle with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Simple, elegant, powerful enough to predict the motion of comets, the wobble of Earth's axis, the exact timing of eclipses centuries into the future. And yet, even Newton admitted he didn't know how it worked. Gravity acted across empty space instantly, with no medium to carry it. This bothered him. It bothered others too. How can the sun reach across 93 million miles of nothing and hold Earth in its grip? Newton's response was pragmatic. I can describe what happens. The why will have to wait. For 200 years, that was enough. Newtonian gravity became the bedrock of physics, engineering, astronomy. It worked so well that questioning it seemed unnecessary. The universe ticked like clockwork, predictable and precise. But the universe, as we're about to see, had other plans. Because in the early 1900s, a young patent clerk in Switzerland was thinking about light and time and the strange ways they behave near massive objects. And when he finished thinking, gravity would never look the same again. The invisible architecture was about to reveal a deeper blueprint, one written not in forces and pulls, but in the very fabric of space and time themselves. Picture a garden in the English countryside, summer fading into autumn, 1666. London is burning with plague. Universities are closed. A young man sits alone beneath the trees thinking. He's 23 years old, unknown, unremarkable to anyone who might pass by. But inside his mind, the universe is beginning to unlock itself. An apple falls. Maybe it really happened. Maybe it's just a story he told later when he was old and famous and people wanted origin myths. Either way, something shifted in that moment. A question formed, simple, devastating. What if the force pulling that apple downward is the same force holding the moon in the sky? That question would change everything. Not immediately, not dramatically, but slowly, carefully, with the patient precision of mathematics, Isaac Newton would prove that heaven and earth operate by the same invisible law. And in doing so, he would give humanity its first true glimpse of gravity's architecture. The apple story has become legend, but here's what we know for certain. Newton returned to his family manor in Woolsthorpe during the plague years, escaping Cambridge's empty halls. He had time, silence, solitude. And in that quiet, his mind wandered into territories no one had mapped before. He wasn't trying to discover gravity. He was trying to understand motion forces, the way objects interact when nothing seems to touch them. He knew Kepler's laws. Planets orbit in ellipses. They move faster when close to the sun, slower when far away. But why? What invisible hand guides them? Kepler had guessed at magnetism, some occult force streaming from the sun. Descartes imagined invisible vortices swirling through space, carrying planets like leaves in a current. Everyone had theories. No one had proof. Newton approached it differently. He thought about the moon. If you throw a stone, it arcs through the air and falls to Earth. Throw it harder, it goes farther before landing. Throw it impossibly fast, and theoretically it would curve around the Earth, never hitting the ground, perpetually falling, but always missing. Isn't that what the moon does? Falls toward Earth constantly, but moves sideways fast enough that it never crashes. What if orbits are just falling endlessly in a perfect balance of speed and distance? It's such an elegant thought. The moon isn't defying gravity. It's surrendering to it, completely falling in a curve that never ends. But if that's true, then the same force pulling apples must also pull the moon. And if it pulls the moon, it must pull everything. The sun holds planets. Planets hold moons. Even apples falling through air are responding to the same universal principle. One law, one force, everywhere. Newton called it the universal law of gravitation. Every object in the universe attracts every other object with a force proportional to the product of their masses, and inversely proportional to the square of the distance between them. In mathematical terms, F equals G times M1 times M2 divided by R squared. It sounds abstract cold, but it describes something astonishingly intimate. Right now, you are pulling on the moon. The moon is pulling on you. The force is unimaginably tiny, but it's there. You and the moon are connected by invisible threads of attraction woven through the fabric of space. Every atom in your body pulls on every atom in the earth. The earth pulls back. That mutual attraction is what we call weight. You're not heavy because gravity pushes you down. You're heavy because you and the earth want each other mathematically, inevitably. Does that change how it feels knowing that Newton didn't publish his discovery right away? He was cautious, introverted, prone to paranoia about criticism. He worked in private, refining his calculus, testing his equations against astronomical data, making sure everything aligned. Meanwhile, Robert Hooke, another brilliant English scientist, was making similar claims. Hooke suggested that gravity weakened with distance according to an inverse square law. He wrote to Newton proposing collaboration. Newton bristled. He saw Hooke as a rival, someone trying to claim credit for vague ideas without doing the rigorous mathematical work. The tension between them grew bitter. Hooke accused Newton of stealing. Newton responded with cold fury, minimizing Hooke's contributions, refusing to acknowledge him in published work. When Hooke died in 1703, Newton became president of the Royal Society, and according to some accounts, ensured that Hooke's portrait was removed and lost. Petty, perhaps, but it shows how personal scientific discovery can be, how much ego and insecurity tangle with truth-seeking. Here's the uncomfortable reality: both men contributed. Hooke had the insight, Newton had the proof. Science is rarely one person's triumph. It's a collaborative argument across time, with credit often going to whoever shouts loudest or lives longest. But let's return to what Newton actually achieved. In 1687, after years of solitary work, he published Philosophiae Naturalis Principia Mathematica, the Principia. It's one of the most important books ever written. Dense, difficult, written in Latin, filled with geometric proofs that take hours to unpack. But within its pages lies the skeleton key to celestial mechanics. Newton showed that Kepler's laws weren't arbitrary. They were consequences of gravity. Planets orbit in ellipses because gravity weakens with distance. They speed up when closer to the sun because the gravitational pull is stronger there. Everything Kepler observed, Newton explained, and more. He explained tides, how the moon's gravity pulls on Earth's oceans, creating the rhythmic rise and fall we see twice daily. He explained why the Earth bulges slightly at the equator, why comets follow elongated paths through the solar system, vanishing for decades before returning exactly on schedule. In 1705, Edmund Halley used Newton's equations to predict that a comet seen in 1682 would return in 1758. Halley himself didn't live to see it, but on Christmas night 1758, the comet reappeared blazing across the sky precisely as Newton's math foretold. It was proof. The heavens were predictable. The universe operated by law, not whim. Suddenly, humanity could forecast eclipses, centuries in advance, navigate oceans with precision, discover planets no one had ever seen. In 1846, astronomers noticed that Uranus wobbled slightly in its orbit, as if something invisible was tugging on it. Using Newton's equations, they calculated where an unknown planet must be to cause that wobble. They pointed their telescopes at that exact spot, and there it was, Neptune, a planet discovered not by looking, but by math, by trusting that gravity's invisible hand operates everywhere, always according to Newton's elegant equation. Think about that. A man sitting in a garden in 1666 pondering apples and moons gave humanity the tools to find worlds they'd never imagined. But Newton knew his law was incomplete. It described what gravity does, but not what it is. How does the sun reach across 93 million miles of empty space and hold the Earth in orbit? There's nothing between them. No rope, no medium, no substance. How can a force act across nothing? Newton admitted he had no answer. "I frame no hypotheses," he wrote. He could describe gravity mathematically, predict its effects with stunning accuracy, but the mechanism remained hidden. It was enough to know that it worked. The why would have to wait for someone else. Still, there were cracks in the foundation, tiny ones. Mercury, the closest planet to the sun, orbited slightly wrong. Its ellipse rotated over time, a slow drift called precession. Newton's equations predicted most of it, but not all. There was a tiny discrepancy, just 43 arcseconds per century. Barely noticeable, but real. Astronomers suggested an undiscovered planet even closer to the sun, tugging on Mercury. They called it Vulcan and searched for decades. They never found it. Because Vulcan didn't exist. The error wasn't in the missing planet. It was in Newton's law itself. Not wrong exactly, but incomplete. For over 200 years, Newtonian gravity reigned supreme. Engineers used it to build suspension. Bridges calculate trajectories, design machines. It was the bedrock of physics, unquestioned and seemingly unquestionable, until a young man working in a Swiss patent office started thinking about light and time, and what happens when you fall. His name was Albert Einstein, and he was about to propose something so strange, so counterintuitive, that even he struggled to believe it at first. Gravity, he would suggest, isn't a force at all. It's not something pulling you toward the Earth. It's the shape of space itself, bending around mass, guiding you along invisible curves you can't escape. You're not being held down. You're falling freely through curved space-time, and the ground just happens to be in your way. Imagine that. Everything Newton built, everything that worked so perfectly for centuries, was a shadow. A very accurate shadow, but still just a silhouette of something deeper. And in 1915, Einstein would pull back the curtain and show us what's really there. Not threads of force stretching through the void, but the void itself warped and folded by the presence of mass. Time running slower near heavy objects. Light bending around stars. Space breathing, flexing, rippling with waves we couldn't detect for another 100 years. Newton gave us the map. Einstein showed us the map was drawn on a surface that curves, and that curvature, silent, invisible, omnipresent, is where we're headed next. Into the heart of the strange truth. The place where apples and moons and galaxies all fall together, not because something pulls them, but because existence itself is shaped by their presence. The invisible architecture goes deeper than Newton ever dreamed, and we're about to step inside. Imagine falling. Not the terrifying kind, but the quiet kind. You're in an elevator and the cable snaps. For a few seconds before fear takes hold, you feel something strange. Weightlessness. Your stomach lifts. Your arms float. You're not being pulled down anymore. You're just moving freely through space. In that moment, gravity disappears. Or does it? What if I told you that falling is the most natural state in the universe, that when you're standing still, you're actually the one fighting against the way things want to be? Albert Einstein thought about this. And what he discovered turned Newton's universe inside out. In 1907, Einstein called it the happiest thought of my life. He imagined a painter falling from a roof. During the fall, the painter feels no gravity. If he drops his brush, it falls alongside him, at the same speed, hovering in midair relative to his hand. To the painter in that brief moment, gravity has vanished. Of course, someone watching from the ground sees something different. They see the painter and the brush both falling, accelerating downward. But to the painter himself, everything feels weightless, as if he's floating in deep space. Einstein realized something profound. Falling freely and floating in space are indistinguishable. There's no experiment you could do, no measurement you could take that would tell the difference. Gravity in the moment of free fall ceases to exist as a force you can feel. It's only when something stops your fall, the ground to floor, the seat beneath you, that you experience weight again. This simple thought experiment cracked open a question that would obsess Einstein for the next 8 years. If gravity disappears when you fall, what is it really? Newton said, gravity is a force pulling objects toward each other across empty space. But forces are things you feel. Push a wall and the wall pushes back. Pull a rope and tension runs through it. But gravity. You only feel gravity when something prevents you from falling. The Earth's surface pushes up against your feet, and that resistance is what you interpret as weight, but the falling itself. That's effortless, natural, the default state of existence. What if Einstein wondered gravity isn't a force at all? What if it's geometry? By 1915. After years of intense mathematical struggle, Einstein published his theory of general relativity. It was a radical reimagining of reality. Space and time, he proposed, aren't separate static things. They're woven together into a four-dimensional fabric called space-time. En masse, anything with substance from a pebble to a star warps that fabric. Imagine a trampoline stretched tight. Place a bowling ball in the center, and the surface curves downward, creating a depression. Now, roll a marble nearby. It doesn't fall straight toward the bowling ball because the ball is pulling it. It falls because the surface is curved, and the marble is simply following that curve. It's responding to the shape of the trampoline, not a force emanating from the ball. This is what mass does to space-time. The sun doesn't pull the Earth with invisible threads. The sun curves space-time around itself, and the Earth moves through that curvature, tracing what we perceive as an orbit. You're not stuck to the ground because gravity pulls you down. You're following the curve that Earth's mass creates in space-time. The ground interrupts your path, and that interruption is what you feel as weight. It sounds like poetry, like metaphor, but it's measurable, testable, real. In 1919, just 4 years after Einstein published general relativity, the universe offered a chance to test it. A total solar eclipse would pass over the island of Principe, off the coast of West Africa, and across Sobral in Brazil. During the eclipse, stars near the sun would become visible in the darkened sky. According to Newton, light travels in straight lines unaffected by gravity because photons have no mass. But according to Einstein, light doesn't need mass to be influenced by gravity. It simply follows the curvature of space-time. And space-time near the sun is deeply curved. So starlight passing close to the sun should bend, making stars appear slightly shifted from their true positions. Arthur Eddington, a British astronomer, led an expedition to Principe to photograph the eclipse. It was a fraught mission. World War I had just ended. Einstein was German. Eddington was English. Testing a German scientist's theory felt politically uncomfortable, but Eddington believed in the purity of science and the idea that truth transcends borders. He set up his equipment and waited for the moon to slide across the sun's face. The weather was terrible. Clouds threatened to ruin everything. But in the final moments of totality, the clouds parted just enough. Eddington captured his photographs. When he compared the positions of stars during the eclipse to their positions at night, he found what Einstein predicted. The stars had shifted, light had bent, space-time was curved. The announcement made headlines worldwide. "Newton overthrown," declared one newspaper. Einstein became an instant celebrity, his wild hair and gentle eyes appearing on magazine covers. But here's the key. Newton wasn't overthrown. He was refined. Newtonian gravity still works beautifully for most situations. We still use his equations to launch satellites, predict planetary motion, navigate spacecraft. Newton's law is an excellent approximation when gravity is weak and speeds are slow. But Einstein's theory goes deeper, revealing what's actually happening beneath the surface. Think of it like this. If you draw a triangle on a flat piece of paper, the angles add up to 180 degrees. That's Euclidean geometry, the kind we learn in school. But draw a triangle on the surface of a sphere, say on a globe, and the angles add up to more than 180 degrees. The geometry is different because the surface is curved. Neither geometry is wrong. They're just describing different surfaces. Newton's gravity assumes space-time is flat. Einstein's gravity reveals that space-time curves. Both are useful, but only one explains what happens when gravity gets strong, when speeds approach light, when mass condenses into black holes. And here's where it gets beautifully strange. Time itself bends. According to general relativity, time runs slower in stronger gravitational fields. If you stand at sea level, your watch ticks slightly slower than if you stand on a mountaintop. The difference is minuscule nanoseconds over a lifetime, but it's real. Clocks on GPS satellites orbiting Earth tick faster than clocks on the ground because they're farther from Earth's mass, experiencing weaker gravity. If engineers didn't account for this relativistic time, dilation GPS coordinates would drift by several miles per day. Your phone's map app works because Einstein was right about curved space-time. Astronauts aboard the International Space Station age slightly slower than people on Earth. Not much, just a few milliseconds over months. But it's measurable. Time is not a universal constant ticking uniformly everywhere. It's flexible, malleable, shaped by mass and motion. Imagine two twins. One stays on Earth. The other boards a spaceship and travels near a black hole where space-time is violently curved and time crawls almost to a halt. The twin near the black hole might experience a few hours while decades pass on Earth. When they reunite, one twin is elderly, the other still young. It's called the twin paradox, though it's not really a paradox. It's just how time works in a curved universe. Does that make you feel small or impossibly vast? That time itself is a landscape you move through, not a river carrying you. Einstein's equations are elegant but ferociously complex. 10 interrelated equations describing how mass and energy curve space-time, and how that curvature dictates the motion of mass and energy. Solving them exactly is nearly impossible for most real-world situations. Even Einstein struggled. He spent years working through the mathematics, making mistakes, doubting himself, almost giving up. At one point, he thought he had found a flaw that invalidated the whole theory. He was wrong about the flaw, but the fact that he questioned himself shows how strange and counterintuitive this framework is. Even its creator wrestled with belief. One of the first exact solutions came from Karl Schwarzschild, a German physicist serving on the Russian front during World War I. In the trenches surrounded by war, he solved Einstein's equations for a perfectly spherical, non-rotating mass. What he found was eerie. If you compress enough mass into a small enough space, space-time curves so severely that nothing, not even light, can escape. A boundary forms an event horizon beyond which the universe disappears from view. Schwarzschild had mathematically described what we now call a black hole, though he didn't live to see the term coined. He died of an autoimmune disease just months after publishing his solution, his contribution preserved in equations that still bear his name. Einstein didn't believe black holes could actually exist. He thought they were mathematical curiosities, artifacts of extreme assumptions that nature would never permit. But nature, as usual, had other plans. In the 1960s, astronomers began detecting strange X-ray sources in the sky, compact objects devouring nearby stars, emitting radiation from superheated gas spiraling toward oblivion. Black holes weren't fiction. They were real, lurking in the cosmos, warping space-time into knots so tight that even light surrenders. But we're getting ahead of ourselves. Before we fall into black holes, let's linger on the elegance of what Einstein revealed. Gravity isn't a force, it's the shape of existence. Mass tells space-time how to curve. Space-time tells mass how to move. It's a conversation, a feedback loop, a dance between matter and the stage it performs on. You right now are bending space-time, just a little, an imperceptible dimple in the fabric of reality. And space-time is telling you how to move, guiding your atoms, your cells, your breath. Every heartbeat follows a geodesic, the straightest possible path through curved space. You think you're sitting still, but you're actually moving through time at the speed of time, tracing a line through four-dimensional space-time that feels from the inside like rest. It's dizzying, humbling, the realization that you're not on top of the universe standing firm. You're woven into it, inseparable from the geometry that shapes stars and galaxies and the light traveling between them. And light, massless, swift, still bends. That's where we're headed next. Into the strange territory where photons, which should travel in perfect straight lines, curve around stars, loop around black holes, and reveal galaxies hiding behind galaxies. Because even light obeys the architecture. Even light falls. The invisible threads go deeper still, and we're just beginning to pull them. Light has no mass. It's pure energy racing through the void at 186,282 miles per second, the universal speed limit. Nothing catches it. Nothing slows it. It should travel in perfect straight lines, indifferent to the gravity that pulls on planets and moons and falling apples. And yet, light bends. It curves around stars, loops around black holes. And sometimes it shows us galaxies that shouldn't be visible at all, hidden behind other galaxies, their light twisted and magnified by the warping of space itself. How does something weightless fall? What does it mean when even light obeys gravity's invisible hand? Einstein predicted it. In his equations, mass doesn't just pull on other mass. It curves space-time, and anything moving through that curved space, planets, comets, even massless photons, follows the curve. Light doesn't need weight to be affected by gravity. It just needs to travel through a universe that isn't flat. And our universe, shaped by stars and galaxies and the dark matter threaded between them, is anything but flat. The first proof came in 1919 during that solar eclipse we touched on earlier. But let's go deeper into what actually happened, because the story is more fragile and more beautiful than the headlines suggested. Arthur Eddington sailed to Principe, a tiny island off the west coast of Africa, carrying heavy photographic equipment and a quiet hope that Einstein might be right. The war had just ended. Nationalism still simmered. Testing a German scientist's radical theory felt politically fraught. But Eddington was a Quaker, a pacifist, someone who believed science transcended borders. He wanted truth, not victory. The day of the eclipse was cloudy. For hours, Eddington watched the sky, worried that clouds would ruin everything. Then, just as the moon began to cover the sun, the clouds thinned. Not entirely just enough. He took his photographs, 16 plates in total, capturing stars that should have been invisible in daylight, but were now revealed in the sun's shadow. When he developed the images weeks later, comparing them to photographs of the same stars taken at night when the sun wasn't nearby, he found it: a shift. Tiny, barely perceptible, but exactly what Einstein's equations predicted. Starlight passing near the sun had bent by 1.75 arcseconds. A minuscule angle, but enough to prove that space itself curves. Newspapers erupted. Revolution in science, declared the Times of London. Newton's ideas overthrown. Einstein became a celebrity overnight, his face suddenly famous, his theories suddenly validated. But here's the quiet truth: only 2 of Eddington's 16 photographic plates were usable. The others were ruined by clouds or focus issues. Some historians suggest Eddington may have unconsciously favored the data that supported Einstein, discarding ambiguous results. Does that tarnish the discovery? Maybe a little. But later experiments confirmed it beyond doubt. Light bends, space-time curves. The 1919 eclipse was just the beginning. Since then, we've seen light bend in ways that reveal the universe's hidden architecture. It's called gravitational lensing, and it's one of the most powerful tools astronomers have. When a massive object, a galaxy, a cluster of galaxies, even a black hole sits between us and a more distant light source, the massive object's gravity warps space-time, bending the light from the background source around it. Sometimes this creates multiple images of the same distant object smeared and distorted into arcs or rings. Sometimes it magnifies distant galaxies that would otherwise be too faint to see, turning gravity into a cosmic telescope. One of the most famous examples is the Einstein cross. In 1985, astronomers discovered a quasar, an intensely bright distant galaxy powered by a supermassive black hole whose light was being lensed by a closer galaxy directly in our line of sight. Instead of seeing one quasar, we see 4 identical images arranged in a perfect cross around the lensing galaxy. It's not 4 separate quasars. It's one quasar, its light split and bent by the curvature of space-time, arriving at Earth from 4 different paths. The closer galaxy acts like a lens not made of glass, but of warped space. There's something almost sacred about it, isn't there? Light traveling for billions of years across the expanding universe encounters a galaxy, and instead of being blocked, it's guided around it, bent into multiple paths, all converging on us. We see the same ancient photons from 4 directions at once, a visual echo of gravity's geometry. Einstein himself thought gravitational lensing would never be observed. The effect he believed was too small, too rare. But the universe is larger and stranger than even Einstein imagined. We have now cataloged thousands of gravitational lenses. Some create Einstein rings, perfect halos of light encircling a foreground galaxy. Others produce Einstein arcs stretched and smeared like brushstrokes across the sky. Each one is a fingerprint of mass, revealing where dark matter clusters, where galaxies hide, where space-time curves most severely. And then, there are black holes, the most extreme lenses in the universe. A black hole is what happens when gravity wins completely. When a massive star runs out of fuel, it can no longer resist its own gravitational collapse. The core implodes, compressing matter into a point of infinite density called a singularity. Around that singularity, space-time curves so steeply that a boundary forms the event horizon. Cross that boundary, and you can never return. Not because something pulls you in, but because every direction you could move, every possible path through space-time leads inward. Even light once past the event horizon cannot escape. It spirals down, following the geometry into the singularity where space and time break down into something we don't yet understand. Outside the event horizon, though, light can still orbit. There's a region called the photon sphere, where light moves in a perfect circle around the black hole. If you could somehow stand there and look sideways, you'd see the back of your own head, because light would loop all the way around. It's a dizzying thought. A place where geometry folds so tightly that vision curves into itself. In 2019, humanity captured the first image of a black hole's event horizon. It wasn't easy. The black hole located in the galaxy M87 is 55 million light-years away and unimaginably massive, 6.5 billion times the mass of our sun. But even something that monstrous appears tiny in the sky, about the size of an orange on the moon as seen from Earth. To photograph it, astronomers linked radio telescopes across the globe, creating a virtual telescope the size of the Earth itself. They called it the Event Horizon Telescope. What they captured is now iconic, a glowing orange ring surrounding a dark circle. The ring is superheated gas accelerated to nearly the speed of light as it spirals toward the event horizon, emitting radiation in its final moments before disappearing forever. The dark circle in the center isn't the black hole itself. It's the shadow cast by the event horizon, a region where light can't escape, where space-time is so warped that visibility ends. The image is blurry, grainy, almost abstract, but it's real. It's a photograph of curved space-time, of gravity's ultimate expression, of a place where the universe folds in on itself and vanishes from view. Think about that for a moment. We've photographed the edge of nothingness, the place where light surrenders. But gravitational lensing doesn't just show us black holes. It reveals something even more mysterious: dark matter. Astronomers noticed decades ago that galaxies spin too fast. The outer stars orbit at speeds that should fling them into space based on the visible mass of the galaxy. Something invisible must be holding them in place, adding gravitational pull without emitting light. We call it dark matter, though we don't know what it is. It doesn't interact with light. It doesn't emit radiation. We only know it's there because of how it bends space-time. When astronomers map gravitational lensing around galaxy clusters, they can trace the distribution of dark matter. The lensing patterns reveal invisible halos of mass surrounding and interpenetrating galaxies far more massive than the stars and gas we can see. Some estimates suggest dark matter makes up about 85% of the universe's total mass. We live in a cosmos dominated by something we can't see, touch, or fully understand. We only know it's there because light bends around it. Does that unsettle you? That most of the universe is invisible, known only through its gravitational fingerprint. Gravitational lensing also lets us peer back in time, because light takes time to travel. Looking at distant objects means seeing them as they were billions of years ago. Some of the most distant galaxies we've observed are only visible because their light has been magnified by foreground galaxy clusters acting as natural telescopes. Without gravitational lensing, those ancient galaxies would be too faint to detect. Gravity, in a sense, helps us see the universe's infancy bending light across billions of years to reach our eyes. The James Webb Space Telescope, launched in 2021, uses gravitational lensing to study some of the earliest galaxies ever formed. By pointing at massive galaxy clusters, astronomers can see beyond them, magnified and distorted, to galaxies that formed just a few 100 million years after the Big Bang. These are some of the first stars lighting up after the cosmic dark ages, and we can see them only because gravity itself has become our lens. There's something poetic in that. The same force that holds you to the Earth, that keeps planets in orbit, that crushes stars into black holes, also bends light in ways that let us see deeper into space and time than we ever could alone. Gravity is more than a force, more than geometry. It's a bridge between now and then, between visible and invisible, between what we know and what we're still learning to see. And light, weightless and eternal, travels those bridges faithfully. It doesn't resist. It doesn't question. It simply follows the curves, tracing the invisible architecture laid down by mass and energy arriving at our telescopes, carrying stories from across the universe. Every photon that reaches your eye has traveled through curved space-time, the light from your lamp bent imperceptibly by Earth's gravity. Sunlight curves slightly by the sun's mass before reaching us. Starlight sometimes lensed by galaxies between here and there, splitting and distorting before finally arriving ancient and patient. Even now, as you rest, light is falling all around you, not pulled by force but guided by the shape of existence itself. It's strange to think that light and gravity share this relationship. One is speed, the other is stillness. One is energy, the other is curvature. But they dance together, inseparable, woven into the same fabric. And that fabric, it turns out, isn't just curved, it ripples. Which brings us to something even stranger. If space-time can bend, can it also wave? Can gravity itself move, spreading through the universe like ripples on a pond? Einstein thought. So, he predicted it in 1916, calling them gravitational waves. But he also thought they'd be far too weak to ever detect. He was wrong. In 2015, we heard them. The universe's faintest whisper, traveling for over 1 billion years, finally reaching Earth. And when it did, it changed everything we thought we knew about listening to the cosmos. But that's where we turn next. From light bending around stars to space-time itself, shaking, rippling, singing, with the collisions of black holes 1 billion light years away. On September 14, 2015, at 5:51 a.m. Eastern Time, something extraordinary happened. 2 detectors, one in Louisiana and one in Washington State, separated by nearly 900 miles, vibrated. Not from an earthquake, not from a passing truck. The vibration was impossibly small, smaller than the width of a proton, and it lasted less than 1/4 of a second. But in that brief moment, humanity heard something we'd never heard before. The sound of space-time itself, rippling. 2 black holes, each about 30 times the mass of the sun, had collided 1.3 billion light years away. And the shock wave from that collision, traveling at the speed of light, had finally reached Earth. We didn't see it with telescopes, we felt it. A whisper from the universe carried on waves of gravity itself. Einstein predicted this in 1916, just a year after publishing General Relativity. If mass curves space-time, he reasoned, then accelerating mass should create ripples in that curvature, waves that propagate outward like ripples on a pond when you drop a stone. He called them gravitational waves. But he also thought they'd be far too weak to ever detect. The universe would have to produce something catastrophically violent, colliding black holes, exploding stars, merging neutron stars. And even then, the waves reaching Earth would stretch and compress space by amounts almost too small to measure. Einstein doubted we'd ever build instruments sensitive enough. For once, he underestimated human stubbornness. The quest to detect gravitational waves began in earnest in the 1960s, led by a physicist named Joseph Weber. He built massive aluminum cylinders, each weighing several tons, and suspended them carefully to isolate them from vibrations. The idea was simple. If a gravitational wave passed through, it would stretch and squeeze the cylinder ever so slightly, causing it to ring like a bell. Weber claimed he detected signals. Other scientists tried to replicate his results and couldn't. The signals, if they were real, were buried in noise, seismic rumbles, temperature fluctuations, electronic glitches. Weber spent the rest of his life defending his findings, but mainstream physics moved on. The consensus became clear: detecting gravitational waves would require something far more sensitive. Enter LIGO, the Laser Interferometer Gravitational Wave Observatory. Two identical facilities, one in Livingston, Louisiana, the other in Hanford, Washington. Each consists of two tunnels, each 2.5 miles long, arranged in an L shape. A laser beam is split and sent down both tunnels, bouncing off mirrors at the ends and recombining back at the starting point. Normally, the beams travel the exact same distance, so they arrive in sync, canceling each other out through destructive interference. But if a gravitational wave passes through it, stretches space in one direction, and compresses it in the other, the beams travel slightly different distances. They arrive out of sync, and that tiny mismatch creates a signal. How tiny LIGO is designed to detect changes in distance smaller than 1,000th the diameter of a proton. Imagine measuring the distance to the nearest star and noticing a change the width of a human hair. That's the level of precision required. To achieve it, LIGO's mirrors are suspended by elaborate systems of pendulums to isolate them from ground vibrations. The laser beams are stabilized to near-perfect frequencies. The vacuum tubes are among the largest in the world, emptied of air to prevent even molecules from interfering. And still, the detectors are plagued by noise, distant logging trucks, ocean waves crashing on shores hundreds of miles away, even quantum fluctuations in the laser light itself. For years, LIGO searched and found nothing. Engineers upgraded the instruments, increasing their sensitivity. Scientists refined their algorithms, learning to distinguish real signals from noise. And they waited. Because gravitational waves are rare, or rather detectable ones are. The universe is full of gravitational waves, binary stars, rotating neutron stars. Even the Big Bang itself left a faint background hum, but most are too weak to notice. What LIGO needed was something violent, something cataclysmic. On that morning in September 2015, they got it. The signal appeared first at the Livingston detector, then 7 milliseconds later at Hanford, the time it takes light to travel between them. The waveform was textbook perfect. It started low and slow, then rapidly increased in frequency and amplitude, a pattern called a chirp. Scientists recognized it immediately. Two black holes spiraling toward each other, orbiting faster and faster as they lose energy to gravitational waves until finally they merge in a collision so violent it shakes space-time itself. The data told a story. The black holes had been orbiting each other for millions of years, gradually drawing closer. In the final seconds, they spun around each other hundreds of times per second, releasing more energy and gravitational waves than all the stars in the observable universe emit in light. Then they merge, forming a single larger black hole. And the newly formed black hole, still trembling from the collision, rang like a struck bell, sending out one final burst of waves before settling into stillness. The collision happened 1.3 billion years ago. Dinosaurs hadn't yet appeared on Earth. Life was mostly single-celled. And across the universe, two black holes, invisible and silent, were dancing toward destruction. The waves they produced traveled outwards, spreading through space at light speed, passing through galaxies, through dust clouds, through the expanding void for over 1 billion years. And on September 14th, 2015, they finally washed over Earth, stretching and squeezing space by less than the width of an atomic nucleus. And we felt it. The discovery was announced in February 2016 after months of verification. Scientists wanted to be certain. They checked for glitches, analyzed the data, independently confirmed that both detectors had seen the same thing. When they finally went public, the response was overwhelming. News outlets around the world covered it. Physicists wept. Because this wasn't just confirming Einstein's prediction. This was opening a new window on the universe. For all of human history, we've studied the cosmos through light, visible light, radio waves, X-rays, gamma rays. But light can be blocked, absorbed, scattered. Gravitational waves pass through everything. They don't interact with matter. They carry information from places light can never reach. The cores of supernovae, the interiors of neutron stars, the moments just after the Big Bang. We'd been looking at the universe. Now we could listen to it. Since that first detection, LIGO has recorded dozens more, each one unique. Some are black hole mergers, others are neutron star collisions. In August 2017, LIGO detected a particularly interesting event. 2 neutron stars, each about 1.4 times the mass of the Sun, but compressed into spheres just 12 miles across, spiraled into each other and merged. The gravitational wave signal was clear, but this time, something else happened. Telescopes around the world turned toward the source and saw light. A gamma ray burst, visible light, infrared, X-rays. It was the first time humanity had witnessed the same cosmic event through both gravitational waves and electromagnetic radiation. Multi-messenger astronomy had arrived. The neutron star collision produced something else too. Heavy elements, gold, platinum, uranium. Scientists believe that most of the heavy elements in the universe, those heavier than iron, are forged in neutron star mergers. The gold in your ring, the platinum in electronics, the uranium in nuclear reactors. All of it came from collisions, like this one scattered into space as debris eventually coalescing into planets, into Earth, into you. You're wearing the remnants of ancient catastrophes carried across billions of years, shaped by gravity's most violent dance. Have you ever thought about that? That the atoms in your body were once inside stars, and before that, hurled through space by colliding neutron stars, their gravitational waves rippling through the cosmos long before Earth existed. LIGO isn't alone anymore. Europe has built Virgo, a similar detector in Italy. Japan is constructing KGRA buried underground to reduce noise. India plans its own. By combining data from multiple detectors, scientists can triangulate the source of gravitational waves more precisely, pinpointing where in the sky the event occurred. The more detectors we have, the better we can map the universe's violent events, the more we can learn about black holes, neutron stars, and the fabric of space-time itself. But there's a limitation. Ground-based detectors like LIGO are sensitive to high-frequency gravitational waves, those from stellar-mass black holes and neutron stars. But supermassive black holes, the giants at the centers of galaxies, merge too slowly. Their gravitational waves oscillate at much lower frequencies below what LIGO can detect. To hear those, we need a detector in space. Enter LISA, the Laser Interferometer Space Antenna. Planned for launch in the 2030s, LISA will consist of 3 spacecraft flying in formation separated by 1.6 million miles, forming a triangle in space. Lasers will bounce between the spacecraft, measuring tiny changes in distance caused by passing gravitational waves. LISA will be sensitive to low-frequency waves, opening a window on supermassive black hole, mergers binary systems throughout our galaxy, and possibly even the faint background of gravitational waves left over from the Big Bang itself. Imagine that. Listening to the birth of the universe not through light, but through the ripples in space-time created in the first fractions of a second after everything began. The cosmic microwave background shows us the universe 380,000 years after the Big Bang, when light could finally travel freely. But gravitational waves could in theory carry information from much earlier, from the inflationary period, when the universe expanded faster than light, stretching quantum fluctuations into cosmic structures. If we can detect those primordial waves, we'll be hearing echoes from the very beginning of time. Gravitational waves also test general relativity in extreme conditions. Einstein's equations predict exactly how waves should behave, how their frequency and amplitude change as black holes spiral inward, how they carry energy away, how space-time itself vibrates in response to mass. So far, every detection matches the predictions. General relativity more than a century old still holds. But scientists keep testing because the strongest gravity lies in the places we've only just started to probe. Near merging black holes, inside neutron stars, at the edge of event horizons. If Einstein's theory breaks down anywhere, it'll be there in the extremes. And gravitational waves give us a way to check. There's something almost mystical about gravitational waves, isn't there? They're invisible, intangible, passing through you right now, without resistance. Waves from collisions billions of years ago, stretching and compressing the space between your atoms by imperceptible amounts. You can't feel them, but they're there. The universe is humming with them, a chorus of cataclysms, quiet and constant. And we've only just begun to listen. LIGO has been operational for less than a decade. Imagine what we'll hear over the next century. Thousands of black hole mergers, neutron star collisions, maybe even signals we haven't predicted, exotic objects, unknown physics, the unexpected made audible. The universe has spent billions of years building an orchestra of gravity. We've finally learned to hear it. But even as we listen to space-time ripple, there are mysteries deeper still. Because gravity, for all we've learned, still holds secrets we can't crack. Dark matter, dark energy, the failure of general relativity to merge with quantum mechanics. These aren't small puzzles, they're chasms in our understanding, places where the equations break down and our theories whisper, "I don't know." And that's where we're headed now. Into the dark territories, the questions that keep physicists awake at night. The places where gravity, beautiful and predictable everywhere else, becomes strange and uncooperative. Where the universe itself seems to be hiding something fundamental, something just beyond our reach. Imagine watching a galaxy spin. From Earth through our most powerful telescopes, we can measure how fast stars orbit around the galactic center. According to Newton's laws and Einstein's refinements, stars farther from the center should move slower, just like planets. Farther from the sun, take longer to complete their orbits. But that's not what we see. Stars at the edge of galaxies move just as fast as stars near the center, sometimes faster. It's as if something invisible is holding them in place, adding mass we can't see. Either our understanding of gravity is fundamentally broken, or the universe is hiding most of its matter from us. Both possibilities are unsettling, and one of them is true. In 1933, a Swiss astronomer named Fritz Zwicky was studying the Coma Cluster, a collection of over 1,000 galaxies bound together by gravity. He measured how fast those galaxies were moving relative to each other and did a simple calculation. If gravity comes from the mass, we can see stars' gas dust. Then the cluster shouldn't hold together. The galaxies are moving too fast. They should have flown apart billions of years ago, but they haven't. Something with mass, something invisible, is providing the extra gravitational pull needed to keep the cluster bound. Zwicky called it dark matter, though he had no idea what it was. Most astronomers ignored him. The idea seemed too strange, too convenient. Invisible matter. It sounded like an excuse for incomplete data, but the evidence kept piling up. In the 1970s, astronomer Vera Rubin studied rotation curves of spiral galaxies. She measured the velocities of stars and gas clouds at different distances from galactic centers. Newtonian gravity predicted a clear pattern: velocity should decrease with distance. But Rubin found that velocities stayed flat, even at the outer edges where visible matter thinned to almost nothing. The only explanation was that galaxies are embedded in massive halos of invisible matter, extending far beyond the visible disk. Dark matter, whatever it is, outweighs regular matter by a factor of 5 to 1. 85% of the universe's mass is something we can't see, don't understand, and can only detect through its gravitational influence. Think about that. We live in a cosmos where most of the matter is hidden, transparent to light, passing through ordinary matter without interacting. We only know it exists because galaxies spin wrong and galaxy clusters hold together when they shouldn't. It's humbling, isn't it? To realize that everything we see, stars, planets, nebulae, all the light and beauty in the night sky is just the 5%. The rest is shadows. Physicists have proposed candidates for dark matter. WIMPs, weakly interacting. Massive particles are a popular option. Theoretical particles that barely interact with normal matter except through gravity. Experiments deep underground have searched for WIMPs colliding with detector atoms. So far, nothing. Axions are another possibility, lighter particles predicted by certain extensions of particle physics. But despite decades of searching, we haven't directly detected dark matter particles. We see their gravitational effects everywhere, in galaxy rotation, in gravitational lensing, in the cosmic microwave background. But the particles themselves remain elusive. It's like hearing footsteps in an empty room. You know something's there, you just can't see it. Some scientists propose a radical alternative. Maybe gravity itself works differently on large scales. Maybe Newton and Einstein are right for solar systems and planets, but on galactic scales, gravity behaves differently than we think. This idea is called modified Newtonian dynamics, or MOND. It suggests that at very low accelerations far from massive objects, gravity doesn't weaken as quickly as Newton predicted. This would explain galaxy rotation curves without needing invisible matter. But MOND struggles to explain other observations. Gravitational lensing galaxy cluster dynamics, the cosmic microwave background. Dark matter frustratingly explains more, even if we can't see it. So, we're left with a mystery. Either the universe is full of invisible particles we haven't detected, or our theories of gravity are incomplete in ways we don't yet understand. Both possibilities reshape how we see the cosmos, and neither is comforting. But dark matter isn't the only mystery. There's something even stranger. In 1998, two teams of astronomers were studying distant supernovae exploding stars that serve as cosmic distance markers. They wanted to measure how fast the universe's expansion was slowing down. Because gravity pulling everything toward everything else should gradually slow the expansion over time. Eventually, maybe the universe would stop expanding and collapse back on itself in a big crunch. Or maybe it would expand forever, but more and more, slowly asymptotically approaching stillness. What they found shocked everyone. The universe isn't slowing down, it's speeding up. Distant galaxies are accelerating away from us, moving faster now than they were billions of years ago. Something is pushing the universe apart, overpowering gravity's pull. Something with negative pressure, something that doesn't clump into galaxies or stars, but spreads evenly through space, driving expansion faster and faster. Scientists call it dark energy, though the name is just a placeholder for ignorance. We don't know what it is. We don't know where it comes from. We only know it makes up about 68% of the universe's total energy. Combined with dark matter, that means 95% of the universe is dark unknown, mysterious beyond our current understanding. The simplest explanation for dark energy is the cosmological constant, a term Einstein added to his equations and later called his biggest blunder. When he developed general relativity, the prevailing belief was that the universe was static, unchanging. But his equations predicted that the universe should either expand or contract. To force a static solution, Einstein introduced the cosmological constant, a kind of energy inherent to empty space itself, pushing outward, counteracting gravity's pull. Then, in 1929, Edwin Hubble discovered that the universe is expanding. Einstein realized the cosmological constant was unnecessary and removed it, calling it a mistake, except it wasn't. The cosmological constant, or something very much like it, seems to be real. Empty space has energy, and that energy is pushing the universe apart. Quantum field theory predicts that even a vacuum isn't truly empty. Virtual particles constantly pop in and out of existence, borrowing energy from the uncertainty principle, creating a faint background energy in space itself. But here's the problem. When physicists calculate how much vacuum energy there should be, they get a number that's 10 to the power of 120 times larger than what we observe. That's not a small error. That's the worst prediction in the history of science, off by 120 orders of magnitude. Something is canceling out almost all of the vacuum energy, leaving just enough to drive the universe's accelerated expansion. But we don't know what or why. Does that make you dizzy? That the universe's fate, whether it expands forever, tears itself apart, or collapses, depends on an energy we can't explain. Driven by physics we don't understand, some cosmologists speculate that dark energy might not be constant. Maybe it changes over time, growing stronger or weaker. If it grows stronger, the universe could end in a big rip, where space expands so violently that galaxy stars, planets, even atoms are torn apart. If it weakens, gravity might eventually win, pulling everything back together in a big crunch. Or maybe the expansion continues forever, gently until galaxies drift beyond each other's horizons, stars burn out, and the universe fades into cold, dark silence, a heat death. We don't know which future awaits, and we won't until we understand dark energy. Then there's the other great unsolved problem. Gravity refuses to play nicely with quantum mechanics. The other three fundamental forces, electromagnetism, the strong nuclear force, the weak nuclear force, all fit beautifully into the quantum framework. They're mediated by particles. Photons carry electromagnetism. Gluons carry the strong force. W and Z, bosons, carry the weak force. But gravity? We haven't found its particle. We call the hypothetical particle a graviton. But despite decades of searching, no one has detected one. And it's not clear we ever will, because gravitons, if they exist, interact so weakly that detecting a single one might be impossible. The problem goes deeper. Quantum mechanics deals with probabilities, uncertainty, discrete packets of energy. General relativity deals with smooth, continuous curvature of space-time. When you try to combine them, when you apply quantum mechanics to gravity, the math breaks down. Infinities appear. Nonsensical predictions emerge. Near the center of a black hole where quantum effects and extreme gravity both matter, our equations fail. We don't know what happens at the singularity. We don't know what happened at the very first instant of the Big Bang, before space and time even existed in forms we recognize. The two pillars of modern physics, quantum mechanics and general relativity, are both stunningly successful in their own domains. But they contradict each other at the boundaries. And that means one of them, or both, is incomplete. Physicists have proposed solutions. String theory suggests that particles aren't point-like, but tiny vibrating strings. Gravity, in this view, is just one vibrational mode among many. String theory requires extra dimensions, 10 or 11 total, most of which are curled up so small we can't detect them. It's elegant mathematically, but it makes predictions we can't currently test. Loop quantum gravity takes a different approach, suggesting that space-time itself is quantized, made of discrete units like pixels on a screen. At the smallest scales, the Planck length, about 10 to the power of minus 35 meters space and time, aren't smooth, but grainy, woven from loops of quantum geometry. It's a beautiful idea, but again, testing it is beyond our current technology. Some researchers explore even stranger possibilities. Maybe gravity is emergent, not fundamental. Maybe it arises from deeper quantum entanglement, the way temperature emerges from the motion of molecules. Maybe space-time itself is a hologram, a projection from information encoded on a distant boundary. These ideas sound like science fiction, but they're taken seriously because the problem is real. Gravity and quantum mechanics don't fit together. And until we solve that, we're missing something fundamental about the universe. There's a certain poetry in this. Don't you think humanity has mapped the heavens, detected gravitational waves, photographed black holes, measured the universe's expansion to exquisite precision? And yet, we're still stumbling in the dark, confronted by mysteries we can't solve, questions we can barely articulate. Dark matter, dark energy, quantum gravity. These aren't small gaps in knowledge, they're chasms. Reminders that, for all we've learned, the universe still holds secrets far beyond our grasp. But here's the quiet truth. Science doesn't need to have all the answers to be valuable. The act of questioning, of admitting uncertainty, of searching even when success isn't guaranteed, that's where the beauty lives. Every generation inherits mysteries from the last and passes new ones forward, and maybe that's the point. Not to conquer the unknown, but to live with it, to explore it, to let it humble us. So, we keep searching. We build better detectors, more sensitive telescopes, more powerful particle accelerators. We refine our theories, test our predictions, challenge our assumptions. And sometimes we discover that the universe is even stranger than we thought. That gravity, this invisible force we've studied for centuries, still hides layers we haven't seen. But gravity doesn't just shape galaxies and bend light. It shapes us too. Our bodies, our lives, the rhythms of the planet we call home. And that's where we turn next, toward the intimate, the everyday. The ways gravity touches your life in quiet, constant ways you might never have noticed. Every morning, you wake up and stand. Your heart pumps blood upward against gravity's pull. Your bones bear your weight. Your muscles work constantly just to keep you upright. You probably don't think about it, but your entire body, every cell, every system was shaped by 3.7 billion years of evolution under one gravitational constant, 1g, 8 meters per second squared. Remove that force even briefly and your body begins to forget how to be human. Astronauts returning from months in space need help walking. Their bones are weaker, their muscles have atrophied, their hearts have shrunk. Gravity isn't just something that holds you down. It's the invisible architect that built you cell by cell, generation by generation, into the shape you are. In 2015, NASA astronaut Scott Kelly launched to the International Space Station for a year-long mission. His identical twin brother, Mark Kelly, stayed on Earth. It was a perfect experiment. Same genetics, different gravity. Scientists monitored both brothers, closely tracking changes in gene expression, bone density, muscle mass, vision cognition, immune response. The goal was to understand how long-duration spaceflight affects the human body. Because if we ever want to send astronauts to Mars, a journey that would take 6 to 9 months each way, we need to know what happens when gravity disappears for that long. The results were sobering. Scott lost bone mass about 1 to 2% per month, mostly from his hips and spine. The weight-bearing bones that in space suddenly bear no weight. On Earth, your bones constantly remodel themselves, breaking down old tissue and building new. The stimulus for building is mechanical stress. Walking, running, even just standing, creates tiny stress fractures that signal your body to reinforce the bone. In microgravity, that stress vanishes. Bones stop rebuilding. They become porous, fragile, osteoporotic. Astronauts on the ISS exercise for 2 hours a day on resistance machines designed to simulate weight, but it's not enough. The bone loss continues. After a year, Scott had lost enough bone density that recovery took months and some loss was permanent. His muscles atrophied too, especially in his legs and lower back. Without gravity, you don't need strong legs. Floating is effortless. Astronauts' muscles adapt, shrinking, weakening, redirecting resources elsewhere. Heart muscle shrinks as well. On Earth, your heart works hard to pump blood upward from your legs to your brain. In space, blood distribution changes. Fluids shift toward the upper body and head, creating a puffy-faced appearance astronauts call moon face. The heart doesn't need to work as hard, so it becomes smaller, less efficient. When Scott returned to Earth, his cardiovascular system struggled to readjust. Standing up quickly caused dizziness. His body had forgotten how to fight gravity. Vision changes too. Many astronauts develop a condition called spaceflight-associated neuroocular syndrome. Fluid pressure in the skull increases without gravity, pulling fluids downward. This pressure can flatten the eyeball, causing farsightedness. Some astronauts return with permanently altered vision, requiring glasses for the first time in their lives. Scientists are still trying to understand the full implications. If we send people to Mars, will they lose their vision permanently? Will their brains be affected by prolonged fluid pressure? We don't know yet. Scott's immune system also showed changes. Gene expression shifted. Some genes that regulate immunity turned on or off differently in space compared to Mark on Earth. Most of these changes reversed after Scott returned, but not all. Even his telomeres, the protective caps on chromosomes that shorten with age, behaved strangely, lengthening in space before rapidly shortening after he returned. It's as if his cells were confused about how to age without gravity's constant pressure. The Kelly twins experiment taught us something profound. Gravity isn't just a background condition. It's a physiological necessity. Humans evolved under 1G. Our bodies expect to depend on it. Take it away, and we begin to fall apart, slowly but inevitably. If we want to explore deep space, we'll need artificial gravity rotating spacecraft that create centrifugal force simulating weight. Without it, long journeys become biological gambles. But gravity doesn't just affect astronauts. It shapes every living thing on Earth in subtle, beautiful ways. Plants, for instance, have no eyes, no sense of up or down in the way we do. Yet they always know which way to grow. Roots go down, stems go up. How? Through a process called gravitropism. Inside plant cells are tiny dense structures called statoliths, essentially microscopic stones made of starch. Gravity pulls these statoliths to the bottom of the cell. When a plant is tilted, the statoliths shift, signaling the plant to redirect its growth. Hormones called auxins accumulate on the lower side of the stem, causing those cells to elongate, bending the stem upward. The roots do the opposite, bending downward toward the pull of gravity. Scientists tested this in space. They grew plants aboard the ISS, where gravity is effectively zero. The plants became disoriented. Roots grew in random directions. Stems twisted aimlessly. Without gravity's signal, plants lose their sense of direction. On Earth, a seedling can push through soil, navigate obstacles, and find the surface because gravity provides a constant reference point. In space, that reference vanishes. Even water behaves differently without gravity. On Earth, water flows downward pools, and low places forms droplets that drip and splash. In space, water forms perfect spheres held together by surface tension. It doesn't pour. It floats in blobs, wobbling and shimmering like liquid planets. Astronauts drink through straws or squeeze packets because tilting a glass does nothing. There's no down for the water to flow toward. Fire behaves strangely too. Flames on Earth are teardrop-shaped because hot air rises, pulling the flame upward. In microgravity, flames form perfect spheres, burning outward evenly in all directions, sometimes suffocating themselves if not provided with airflow. Gravity shapes even combustion, something so fundamental we rarely think about it. Here on Earth, gravity sculpts landscapes. Mountains can only grow so tall before their own weight causes them to collapse. On Earth, the tallest mountain is Everest, about 29,000 feet. But on Mars, where gravity is only 38% of Earth's mountains, can grow much taller. Olympus Mons, the largest volcano in the solar system, rises 72,000 feet, nearly 3 times the height of Everest. Lower gravity allows larger structures. Similarly, creatures on Earth are size limited by gravity. The largest land animals ever, sauropod dinosaurs like Argentinosaurus, weighed up to 100 tons, close to the theoretical maximum for land animals under Earth's gravity. Any larger and bones would fracture under their own weight. In the ocean where water provides buoyancy, blue whales can reach 200 tons. On a planet with lower gravity, land animals could be even larger. On a planet with stronger gravity, nothing would grow as tall or as heavy. Tides, too, are gravity's handiwork. The moon's gravity pulls on Earth's oceans, creating bulges of water on the side facing the moon and the side opposite. As Earth rotates, these bulges sweep across the planet, causing the rise and fall we call tides. The sun contributes too, though less strongly. When the sun and moon align during new moons and full moons, their gravitational pulls combine, creating spring tides, the highest highs and lowest lows. When they're at right angles during quarter moons, their pulls partially cancel, creating neap tides, less extreme. Coastal ecosystems evolved around this rhythm. Creatures time their spawning, feeding, and migrations by the tides. Humans built civilizations around tidal patterns, using them for navigation, fishing, and trade. Gravity through the moon's pull writes a rhythm into Earth's biology. And there's something even stranger. The moon is slowly moving away from Earth. Tidal friction, the drag of water moving across Earth's surface, transfers angular momentum from Earth to the moon, pushing it outward by about 1.5 inches per year. Billions of years ago, the moon was much closer. Days were shorter, tides were higher, more violent. Fossils of ancient corals show growth rings indicating that 400 million years ago, a year had about 400 days each day, only 22 hours long. Earth spun faster, the moon loomed larger in the sky. Gravity shaping not just space, but time itself. Have you ever wondered what it would feel like to live on another planet? On Mars, you'd weigh 38% of your Earth weight. A 150-pound person would weigh just 57 pounds. Walking would feel bouncy, effortless. You could jump 3 times higher. But over time, your muscles would weaken. Your bones would thin, just like astronauts in space. On the moon, gravity is only 16% of Earth's. Astronauts during the Apollo missions bounded across the surface in great leaping strides, even wearing heavy suits. It looked joyful, almost playful, but the moon's low gravity is too weak to hold an atmosphere. Without air, without water, without the gentle press of 1G, the moon remains barren. Jupiter, on the other hand, is a nightmare. Surface gravity, if Jupiter had a surface, would be 2.5 times Earth's. A 150-pound person would weigh 375 pounds. Standing would be exhausting. Your heart would struggle. Every movement would feel like wading through thick mud. You'd collapse under your own weight. Evolution under Jupiter's gravity would produce low, squat creatures with thick bones and powerful muscles. Nothing tall could survive. Gravity also dictates the shape of planets themselves. Small bodies like asteroids can be irregularly shaped because their gravity is too weak to pull them into spheres. But anything larger than about 600 miles in diameter has enough gravity to overcome structural rigidity and collapse into a roughly spherical shape. That's why planets are round. Gravity pulling equally in all directions molds matter into the most balanced form. Even the air you breathe exists because of gravity. Earth's gravity holds the atmosphere close, preventing it from drifting into space. Mars, with weaker gravity, lost most of its atmosphere billions of years ago, stripped away by solar wind. Earth's stronger pull keeps oxygen, nitrogen, carbon dioxide bound to the surface, creating the envelope of air that makes life possible. Without gravity, our atmosphere would evaporate, and we'd suffocate in the void. So, here's the strange intimacy of it all. Gravity isn't distant. It's not just about galaxies and black holes and the curvature of space-time. It's in your bones, your heartbeat, the way plants grow toward the sun, the rhythm of tides, the air in your lungs. It's been shaping you since before you were born, and it will keep shaping everything long after you're gone. You live inside gravity's architecture, moving through invisible curves held by forces you can't see but feel in every breath, every step, every beat of your heart. And now, as we near the end of this quiet journey, we come full circle, back to the question we started with. What is gravity really? Not the equations or the measurements, not the history or the mysteries, but the feeling of it, the way it holds you, the way it's always been there, silent and patient, weaving the universe together, one atom at a time. We've traveled far tonight, haven't we? From ancient gardens where apples fell to the curved fabric of space-time, to black holes singing across the void. We've walked through centuries of human curiosity, watched scientists stumble and soar, seen light bend, and galaxies spin too fast. We've listened to the universe ripple. We've touched the mysteries that still elude us, dark matter hiding in plain sight, dark energy pushing everything apart, the stubborn refusal of gravity to fit neatly into our quantum equations. And through it all, one invisible thread has held everything together: gravity. The force that isn't really a force, the architecture beneath existence, the gentle hand that's been guiding you, holding you, shaping you every single moment of your life. Right now, as you rest, gravity is working. Your heart is pumping blood upward, fighting against the pull toward your feet. Your lungs are expanding and contracting, lifting your ribs against the weight of the atmosphere pressing down. Your spine is compressing slightly, the discs between your vertebrae bearing the load of your upper body. When you sleep, when you finally let go and lie flat, those discs expand again. You wake up slightly taller than you were when you went to bed. Gravity shapes you differently depending on whether you're standing or lying down. It's always there, patient and invisible, doing the quiet work of holding you together. Every breath you take exists because gravity holds the atmosphere close to Earth's surface. Oxygen molecules, nitrogen, carbon dioxide, they all want to drift away into space, spreading out according to the second law of thermodynamics. But gravity gathers them, keeps them pressed against the planet, creates the thin blue envelope that makes life possible. Without it, the air would vanish. The oceans would boil away into the void. Earth would become another barren rock spinning silently in the dark. But gravity gave us more than air and water. It gave us time, days and nights, seasons. The moon's slow orbit pulling tides that shape coastlines and regulate the rhythms of marine life. The sun's steady hold on Earth, keeping us at just the right distance, not too close, not too far, so that liquid water can exist, so that temperatures stay within the narrow range where life can flourish. If Earth's orbit were 5% closer to the sun, we'd be Venus, a scorched hellscape. 5% farther, and we'd be frozen like Mars. Gravity put us here in this Goldilocks zone and kept us circling for 4.5 billion years, long enough for single cells to become dinosaurs, for dinosaurs to become dust, for that dust to become you. Think about the precision required. The gravitational constant, the number we represent with g in Newton's equation, is one of the universe's fundamental constants. If it were slightly stronger, stars would burn through their fuel, too quickly collapsing into black holes before planets could form, before life could begin. If it were slightly weaker, stars wouldn't ignite at all. Clouds of hydrogen would drift forever, cold and dark, never fusing into the heavier elements that make up your body: carbon, oxygen, nitrogen, calcium, iron. The fact that gravity has the exact strength it does, that the cosmological constant is precisely the value we measure, that the balance between expansion and attraction is just right. It's either an extraordinary coincidence or a hint that we live in one universe among countless others, each with different laws, and we happen to exist in the one where gravity allows complexity structure life. Some physicists call this the anthropic principle. We observe the universe to be compatible with life because if it weren't, we wouldn't be here to observe it. It's circular reasoning, but it's also undeniable. The universe seems finely tuned for our existence. Or perhaps we're just the kind of life that happens to fit the universe we're in. Either way, gravity is part of that delicate balance. Too strong and everything collapses. Too weak and nothing binds. But here in this universe, in this galaxy, on this planet, gravity is just right. And yet, for all its precision, gravity is the weakest of the four fundamental forces. Electromagnetism is vastly stronger. The electromagnetic force holding electrons to atomic nuclei is about 10 to the power of 36 times stronger than the gravitational attraction between those same particles. You can demonstrate this with a simple magnet. A fridge magnet powered by electromagnetic forces can lift a paperclip, overcoming the gravitational pull of the entire Earth. Think about that. One tiny magnet versus the entire planet, and the magnet wins. Gravity is weak. So weak that it only becomes noticeable when you gather enormous amounts of mass planets, stars, galaxies. And even then, it works slowly, patiently over eons. But weakness isn't the same as insignificance. Gravity's weakness is what allows complexity. If gravity were stronger, stars would collapse too quickly. Planets wouldn't form stable orbits. Life, which requires billions of years of stable conditions, would never have time to evolve. Gravity's gentle touch is precisely what makes the universe habitable. It doesn't dominate. It doesn't crush. It holds softly, persistently, giving atoms time to gather into molecules, molecules into cells, cells into trees and oceans, and people who look up at the stars and wonder. There's something almost tender about that, isn't there? The universe could have been dominated by strong forces, violent and quick. But instead, the force that shapes galaxies, that writes the architecture of space-time itself, is the gentlest one. It works in whispers, in curves, in patient accumulation, and it's still teaching us. Right now, scientists are planning missions to test gravity in new ways. The European Space Agency's LISA mission, set to launch in the 2030s, will listen for gravitational waves from supermassive black holes, binary systems, maybe even the Big Bang itself. NASA is developing missions to map dark matter with unprecedented precision, using gravitational lensing to trace the invisible scaffolding of the universe. Physicists are building experiments deep underground, searching for dark matter particles, hoping to finally see the shadows that make up most of the cosmos. And maybe someday we'll crack the quantum gravity puzzle. Maybe we'll find a way to unite general relativity and quantum mechanics, to understand what happens at the singularity of a black hole, to peer into the first moments after the Big Bang, when space and time themselves were born. Or maybe we won't. Maybe some mysteries are meant to stay mysterious reminders that the universe is larger and stranger than any theory we build. But that's okay. Because the journey, the asking, the searching, the slow unraveling of secrets, that's where the beauty lives. Science isn't about having all the answers. It's about being brave enough to ask the questions, humble enough to admit when we're wrong, and curious enough to keep looking, even when the darkness doesn't give up its secrets easily. Gravity has been our guide through that journey for centuries. From Aristotle's flawed certainty, to Galileo's experiments, from Newton's universal law, to Einstein's curved space-time, from LIGO's first detection, to the mysteries still waiting in the dark. Each generation peeled back another layer, revealing something deeper, stranger, more beautiful. And the invisible architecture, the threads that hold galaxies together and pull raindrops to the Earth, continues to shape everything indifferent to whether we understand it or not. So, here we are at the end of this quiet night, drifting through the final thoughts. You've journeyed from ancient gardens to black holes, from the bending of light to the ripples in space-time, from dark mysteries to the intimate ways gravity shapes your body, your breath, your life. And all of it, every equation, every discovery, every unanswered question comes back to this simple truth: you are held. Right now in this moment, gravity is embracing you, not pulling you down, but guiding you through the curve of space-time, keeping you exactly where you need to be. It doesn't ask for thanks. It doesn't demand recognition. It simply is. Constant, patient, invisible, the quiet architect of everything. And maybe that's enough. Maybe it's enough to know that the same force holding you against the Earth also holds the moon in its orbit, the sun in its place, the galaxies in their slow spiral through the dark. You're part of that, connected to it all through invisible threads woven into the fabric of existence itself. That's not loneliness, that's belonging. So rest now. Let gravity do what it's always done. Let it hold you. Let your body sink a little deeper into the curve of space-time, into the gentle embrace that's been there since before you were born and will remain long after you're gone. You don't need to understand it fully. You don't need to solve the mysteries. You just need to trust that the invisible hand, the geometry of existence, will keep you exactly where you're meant to be. We've walked through the universe together, tonight, you and I, through time and space, through the known and the unknown. And now, as the journey softens into stillness, I want to thank you for being here, for listening, for wondering, for letting curiosity drift you gently through the invisible architecture of everything. Gravity holds you even now, as you drift, as you rest, as you finally softly let go. Sleep well, dream gently. And when you're ready for another quiet journey through the cosmos, another story told softly in the dark, I'll be here, waiting, with more mysteries to share, more whispers from the universe, more gentle invitations to wonder. Until then, good night.